Okay, the remainder of this unit is going to have to do with what happens when we don't have a nice pretty polynomial that gives us nice zeros. And the first thing we're going to talk about is non-real zeros. This is actually the problem we left off on the last video here, and the solution we wrote there is the part on the bottom. That's the factored form of f of x. And so what we didn't address in the last video was actually solving for x here, because we factored it, and that's all well and good, but how do we solve for x? Well, it's zero product property states that x could be -1, right? If we set x plus 1 equal to 0 and we solve for x. It also says that x could be 5 because we would set x minus 5 equal to 0. But then what about this part? So we established that this does not factor, and so we could either complete the square or use the quadratic formula. This would be a rare case where I'd recommend using the quadratic formula because I think it's a little simpler than completing the square for this problem. So the quadratic formula says that x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. And so that 2 is a, b is -1, and c is 10, right? So if we plug this in, we will get 1 plus or minus the square root of b squared, which is 1, minus 4 times 2 times 10 is 20, right? And then divide that by 2a, so a is 2, so we have 4 on the bottom, which would give me 1 plus or minus, and then I root 79 over 4, right? That is a negative radicand, so we can take the square root of -1 out of that as an I, and if we can further simplify square root of 79, then we would, but we can't, so we don't. And so that means the zeros, the two zeros here are 1/4 plus I times the square root of 79 over 4, and 1/4 minus I times the square root of 79 over 4. Okay. So the answers then, like, is to solve for x, we'd have x equals -1, x equals 5, and x equals both of these things. Now, interestingly, if we can find the zeros, we can kind of work backwards and say, what would the factors have been, right? Because usually when we say factor, we're talking about factoring over the integers. And so that implies that we're not talking about imaginary numbers or non-real numbers, complex numbers with non-zero imaginary parts. So to work backwards here, all we have to do is think about, like, what was this before it was this? So what was this before it was this? Well, -1 was x plus 1 before it was -1, right? So if I were to move this -1 back to the other side of this x, I'd have what the factor was, right? That's that factor. So we'll do the same thing for these. So x equals 1/4 plus I root 79 over 4. If I move this whole thing back over, what I get is x minus 1/4 minus I times the square root of 79 divided by 4. And on the other one, if you had that, right, x equals 1/4 minus I root 79 over 4, we'd have x minus 1/4 plus I root 79 over 4. This isn't common to write it this way, but technically, if I was just completely factor, like ignoring the fact that the instruction to factor usually implies that we're talking about integers, then I could do this. And so, well, notice how also there are 2 here, and there's always going to be 2. So why is that? Well, to answer that question, we first have to talk about something called the fundamental theorem of algebra. And the fundamental theorem of algebra is pretty fundamental. It's very simple, too. It states that every polynomial function of positive degree n with complex coefficients has exactly n complex zeros. So what that means is if I have a polynomial with, like, the highest degree term is to the 23rd, like x to the 23rd minus 15x to the 19th minus 1, this has 23 complex zeros. And when it says complex zeros, that's a combination of all of the zeros. So that includes real zeros, it includes rational real zeros, it includes irrational real zeros, and it includes non-real zeros. So the total number of solutions to a function is equal to the degree, the highest degree term. And so, how do we apply this to what we've been talking about? Well, we have to add in one extra layer here. And that layer is the conjugate zeros theorem. And what the conjugate zeros theorem says is that if p of x is a polynomial with real coefficients, and if a plus bi, where a and b are real and b does not equal 0, is a 0 of p, then a minus bi is also a 0 of p. Now a plus bi and a minus bi, those should stand out to you as the standard form of a complex number. And usually when we talk about every number is a complex number, and if they have a 0 non-real part, then we just say it's a number. So like 1 is a complex number, but it can be written, you can think of it as 1 plus or minus 0i. And so basically the conjugate zeros theorem says is that complex solutions with non-zero imaginary components always come in pairs. And why is this? Well, we can break this down into the simplest possible situation. Like, what if we had x squared equals -1? Well, to solve for x, we would have to take the square root of both sides, and then we would have the absolute value of x is equal to the square root of -1, right? And so then what we have is that x is equal plus or minus the square root of -1, and we know the square root of -1 to be I. So we say that x is equal to plus or minus I. And so the only way we ever get these non-real solutions is from a quadratic term when we're trying to solve for a quadratic, and x squared in this case being the quadratic. Or you could say x squared plus 1 equals 0 was the original quadratic there, and we want to define the solution. So there will always be two. We will never only have the one. And so to answer this question here, is it possible to have a single complex 0 with a non-zero imaginary component? Like, for example, can 3 plus 2i be the only complex 0 of a polynomial? No, it can't. You would also have to have 3 minus 2i. So let's apply all of that to this chart here and think about this. If we had, first of all, the fundamental theorem of algebra states that if we have a polynomial of degree 1, that means there's 1 0 and it has to be real. Okay, any line has to cross the x-axis somewhere, otherwise it would be a horizontal line. Okay, and that means there's no non-real zeros because we already have the total number of zeros as 1. If we had a second degree polynomial, that means there's 2 total zeros. There is possibly 2 real zeros or 0 real zeros. Okay, you could potentially have like a quadratic floating on space where it doesn't actually cross the x-axis. A real 0 means it crosses the x-axis. A non-real, that means we have 0 non-real zeros and 2 non-real zeros in the case of 0 real zeros. So I'm saying a lot of zeros here, but I'm sorry. So that means in both cases we'd have 2. Now if we had a third degree polynomial, we could have potentially 3 real zeros or just 1. Okay, we could have in the case where we have 3 real zeros, we have no non-real zeros. Okay, and in the case where we had 1 real zero, the other 2 would have to be non-real. In the case where we had a fourth degree polynomial, we could either have 4 real zeros, 2 real zeros, or 0 real zeros. A fourth degree polynomial would have to do something like this, where we'd have 1, 2, 3, 4 real zeros, something like this, where we had 1 or 2, or something like this. Not a good picture, but doesn't cross the x-axis at all. And those are the 4 scenarios there. To finish that off, then we'd have 0, 2, and 4 kind of going backwards, where we end up with 4 total zeros like we should have. And then a fifth degree polynomial would do, we'd have 5, 3, or 1. And it's because they have to be in pairs. Like, notice all of these, this must be an even number here. We could either have zeros and even, but 2 or 4, or potentially more than that, like 6 if it was a 6 degree polynomial. And so in any case, we fill out that chart that way. All right, so what if we had a problem like this? It said find the polynomial that has the following roots. Well, here we have it. We know that this is legit because those two had to come in pairs. And so how do we work backwards and figure out what this polynomial was? Well, what was this before, right? What was the 3 before x equaled 3? Well, x minus 3 had to equal 0. So x minus 3, this factor, this 0 corresponded to the factor of x minus 3. So all we need to do now is figure out what the other two the other two corresponded to. So in that case, we would just say if x equals negative 4 plus 3i, and we subtract everything back to the left side, then x plus 4 minus 3i is a factor. And similarly here, x plus 4 plus 3i is a factor. And so to find the polynomial, what we're going to have to do is just multiply everything out here. So let's multiply these two together here. So we know x times x, so we have x squared plus 4x plus 12i, and then if we go to 4, we'd have plus 4x plus 16 plus 12i. Okay, and then if we go sorry, 3, we have this last one, x times, I messed one up, this would not be 12i, this would be 3xi, okay, and then, let me just fix that, make it look better, that would have been plus 3xi, okay, so 12i, then we have negative 3i times x, so negative 3xi, and then negative 3i times 4 is negative 12i, and then negative 3i times positive 3i is negative 9i squared, which is equal to, because I is negative 1, right, it's equal to 9, so plus 9. So we've got to combine all this stuff. Notice that the 3xi and the negative 3xi are going to cancel out, and the 12i and the negative 12i are going to cancel out. So we would have x squared plus 8x plus 9. That was that combination, that quadratic, produced those two zeros. And then to finish that off, we just multiply that by x plus x minus 3. So we do the same thing here. Okay, we distribute everything. So we'd have x cubed plus 8x squared plus 9x minus 3x squared minus 24x minus 27. Combine like terms, we end up with x cubed, and then we'd have minus 5x squared, 9x minus 24x is negative 15x, and then minus 27. And so that was the original